Okay, welcome to today's class on random matrices. So I would like to remind you where we got to last time. We saw the definition of the protagonist of much of these lectures, at least of this semester, which is the Wigner matrix. So it's a, I recall, so it's an n by n matrix, a Hermitian matrix, and its entries are in general complex numbers, and we choose maximally independent entries under this constraint that the matrix is Hermitian, which means that, for example, the upper triangular entries are all independent, and the remaining ones, the lower triangular ones, are of course given by the constraint that this matrix is Hermitian, and we assume that these entries are centered and they all have the same variance. And we don't really care about the variance of the diagonal entries, so we can allow them to be of order 1 over n, but what the coefficient is doesn't really matter. And we make also this assumption, which is important. I mean, it's a technical assumption, but it plays a certain role, that these entries, they should not have too heavy tails. So the tails should be light in the sense that all moments exist. So that's a relatively, it's a mild but reasonable condition on the tails. It can of course be relaxed a lot if one wishes, but we don't want to go there. So this is the definition from last time. This is, if I recall correctly, this is how far we got. So let me make now one remark. The first one is concerning this 1 over n, or this square root of n here. So why is that the right normalization? If you recall, we take the convention, we would like always to normalize our matrices in such a way that the eigenvalues are typically of order 1. And so of course this is just a normalization of the matrix by some scalar deterministic quantity, so it's in some sense trivial, but I would like to show that this is the correct one, the correct order, and that's an easy calculation. So this is a remark on this normalization. So the eigenvalues, they are typically of order 1. So what does this mean? One way of making this precise is to take an eigenvalue lambda I. So if you recall, this was our notation. The lambda I is the ith eigenvalue of h, which is a real number. I take this guy squared and I average over I. And if the number I get is of order 1, then that's what I mean by saying that these eigenvalues are typically of order 1. So let me take the sum over all of these eigenvalues, and then I divide by n, so I'm averaging. And let me compute the expectation. One could also take higher moments, but let me just consider the expectation. And this is an object that is very easy to compute by the following observation, that this object, the sum of the squares of the eigenvalues, is nothing but the trace of h squared. If you just go to the eigenbasis of h, this is trace of h squared, and this you can write in terms of the entries So this is in terms of the entries, and now maybe I can bring the expectation inside. And now I just use this condition. So h is Hermitian, so this thing is precisely equal to the expectation of hij squared. So this is equal to 1 plus which means you get precisely, this thing is precisely equal to 1 plus big O of 1 over n. Okay, but you see this 1 over n is important. That's the thing that guarantees that this is of order 1. In fact, it's equal to 1 plus a term of order 1 over n. Okay, is this all right? So this shows that this is the good normalization, and hence also this one to put in front of my matrix. Okay, so examples. I mean, there are of course, you can pick any of your favorite probability distributions. You can put it in here. You can put it in Hij, and you will have an example. So giving examples is kind of artificial. Let me nevertheless mention the Gaussian examples because they are important. So these, the GOE and the GUE that we saw last time, they are examples of Wigner matrices. Now, Wigner matrices with Gaussian entries. And you can check, it's in fact a little exercise you can do if you wish, with Gaussian variables to check these conditions. You can. I won't do this because it's very easy, but if you want to work through this definition, you can check that the GOE and GUE we defined last time indeed satisfy these conditions. And in particular, you will see that for GOE, allowing this extra freedom is important. So for GOE, the variance of the diagonal entries is in fact 2, whereas the variance of the off-diagonal ones is 1, divided by n always. Okay. Good. So that was Wigner matrices. Now let me define a simple probability distribution on the real line, which will turn out to describe the density of the eigenvalues of these matrices. So this is this famous semicircle law of random matrix theory. So as its name implies, it's a, what we call it, semicircle distribution. So as its name implies, it's a probability distribution whose density is a semicircle. So let me denote it by rho. Okay, so it's precisely it's a semicircle, and this is the right normalization, right? The total area of this semicircle is 2 pi, so I normalize it by 2 pi, and I get a probability density. So this plus means the positive part. So this law vanishes outside of the interval -2, 2. And the Stieltjes transform, if you recall, we had these conventions which I will stick to throughout the course. So we had, this is just reviewing notation from last time, mu was the empirical eigenvalue measure of the matrix H. And from now on, H is going to be a Wigner matrix. So mu is now going to be a random probability measure, which is the empirical eigenvalue measure of H. And rho was whatever deterministic law I choose with density. And from now on, it's going to be this, the semicircle. And then they had Stieltjes transforms, which were called G, which was the Stieltjes transform of mu. And M was the Stieltjes transform of rho. So with Stieltjes transform, the Stieltjes transform given by called M. Okay, so this is just a definition. The main goal of the first half, or the first third maybe, of this semester is to show that mu and rho are close, or in the language of Stieltjes transforms, M and G are close, in a very, very strong sense. And that the fact that this sense is going to be very strong is extremely important for all of the applications we will discuss subsequently, including universality, distribution of eigenvalues on small scales, and information about eigenvectors. So this quantity M, if you recall the definition of the Stieltjes transform, so let me write it here. I mean, this is reviewed. So M of Z is equal to the integral rho dx x minus Z. So this is an extremely explicit integral, right? You just take this function, square root of 4 minus x squared, you integrate it from minus 2 to 2 with respect to x minus z. Z is a complex number. So this is an explicit integral. In fact, one can do it. There's a variety of ways of doing it. You can do it using complex analysis. You can do it using power series. And the answer is the following. So M of Z is equal to the following explicit expression. So it is minus Z plus square root of Z squared minus 4 divided by 2. Now I have a square root of a complex number, so one has to be slightly careful. So one has to define which square root do I take, or in other words, where is the branch cut, and I always choose the standard branch of the square root, which means it has a branch cut on the negative real axis. So this is not very surprising. What does it mean? If this square root has a branch cut on the negative real axis, it means this function has a branch cut when this is on the branch cut when this number is negative, which means when z is a real number between minus 2 and plus 2. That means this is an analytic function in the complex plane with a branch cut precisely in this interval, minus 2 plus 2. And that makes sense if you recall the definition of the Stieltjes transform. The Stieltjes transform is well defined everywhere except on the support of the measure. And the support of this measure is precisely the segment minus 2, 2. So this is at least coherent with this definition of the Stieltjes transform. And now in particular, this looks very much like the solution of a quadratic equation, and in fact it is one. So in particular, you can easily check that this is a solution of this quadratic equation. And in fact, so this quadratic equation in general has two solutions, and it has one. So when the solutions are distinct, precisely one of them is in the upper half plane and the other one is in the lower half plane. And this is the unique. This can also be characterized as the unique solution of this quadratic equation in the upper half plane. The Stieltjes transform, this was an exercise from last week. We saw if z, so I always assume z is in the upper half plane, then this number always lies in the upper half plane, right? You can just take the imaginary part here, and it's basically the calculation we did last week. This number will also have positive imaginary part. So this can also be characterized as and 4, I should say 4. You recall H, this bold-faced H, was the complex upper half plane. It's the unique solution of this quadratic equation in the complex upper half plane. The other one would have a minus here. So the other solution would be the one with minus. And you can check easily that the imaginary part of this number would be negative if you take the minus. So this is an exercise which is, so it's going to be on the next problem set. It's not, I mean, in principle, it's elementary calculation, which you could, in principle, have done after your first year of analysis or calculus. But it's not completely trivial, so you have to, you may have to, I mean, you can't, it's not a two-line exercise, it's maybe a one-page exercise, so that's why I will put it on the next exercise set, maybe with some hints. But in principle, there's nothing deep. It's completely elementary stuff. So this is something we will use, and in fact, this characterization as the unique solution of this quadratic equation with positive imaginary part is the one we will usually use. It's the more convenient characterization of M. Is this okay so far? Any questions? So if there are any questions, you should interrupt. You should feel free. All right, so before we come to the main result of basically of this semester, in fact, let me introduce a very useful probabilistic way of writing estimates. So it's the following thing. So it goes, in the literature, it goes by the name of stochastic domination. So in the random matrix theory literature. It was perhaps an unfortunate choice of name. There is another notion of stochastic domination from probability, which you may know of, and this has nothing to do with that one. So this is a completely different notion. Maybe we should have chosen a different name, but it's too late to change now. So that's what it's called. So what does it say? The basic idea is very simple. So we will be considering random variables, let's say positive random variables. You can take absolute values. And you will have a random variable x, and you will have a random variable y. And you would like to say that basically x is bounded by y. But this is not quite true. So first of all, you would like to say that this is true only with very high probability. So this is true with high probability, or with very high probability, by which I'll explain in a minute, but by which I mean arbitrarily high polynomial bounds on the error probability. And this is still not quite true. There might be some you want to give yourself some room. So this is going to be up to factors of n to the epsilon, so arbitrarily small epsilon. And this is, in fact, what we want to say. So this is the basic intuition. So we will say that x is stochastically dominated by y if x is bounded by n to the epsilon times y for arbitrarily small epsilon with very high probability. So let me try to make this more precise. So there are a few technicalities which one should worry about if one wants to make this completely precise. So of course there's this n which underlies everything. It underlies this. Of course I have an n to the epsilon. It also underlies the meaning of very high probability. So x is going to be a family indexed by n. That's clear. And I will also, this is going to be very important, I will also want to apply this notion to entire families, so many different random variables. You should think of x maybe as being a matrix, and y as being a matrix, maybe depending on z. And I want this to hold for every I, every j, and every z. But I want, it's very important that this epsilon and whatever meaning I give to this thing do not depend on I, j, and z. So everything has to be uniform in these indices and in the argument z. And all of these indices in the argument z, I will put into some abstract argument u. So this is a family of random variables. N is in n, and u is going to be in some abstract index set, which can depend on n as well. So this is my X, this is a family X, and then I have a family Y. Which are indexed by U and N. So these are families and in fact it's important they are non-negative. So I have two families of non-negative random variables where UN is just is any set, could be uncountable, typically in fact it is. So then we introduce this notion, and if this holds, we will use this notation, so X. It's not very easy. I will try to make it nice the first time I draw it. It's this kind of order relation. It's this symbol that can be used for abstract order relations. In tech, if you write tech, it's this command. So then we say that X is stochastically dominated by Y uniformly in U. Uniformly in U, if, and only if, so for all epsilon, positive epsilon, for all D is going to characterize the notion of very high probability. The probability that X the probability that this is not true is going to be of order n to the minus d. So it has to go to 0 very fast with this arbitrarily high exponent in n, and this is going to be of order, so bounded by some constant. And the implicit constants here, they can depend, in general they will, in fact they basically have to depend on epsilon and d. Right, so you should think of it as the smaller, if you make epsilon smaller and smaller and d bigger and bigger, then these implicit constants become bigger and bigger. Okay, but for any fixed epsilon and if any fixed d, you can find some constant such that this is true for all n. And I still have a u. And this is the notion of uniformity. So this holds, you can take the supremum over u, this holds uniformly for all u. Okay, note that this is not the same thing as saying that the probability that this thing holds for all u is smaller than that. This is a weaker statement. This is a uniform bound on the probability. It's not a simultaneous bound. Is it clear? Right? So that would be a stronger statement. If instead of having a sup here, I would say the probability that for all u, the probability that there exists a u such that this thing holds is bounded by that. That would be a strictly stronger statement. That would be a simultaneous statement. I mean, if you've studied stochastic processes, then you know these distinctions. But this is what I mean. So maybe at this point, I should have a pause and ask if everything is clear. Is this definition, does it make sense to you? So you should really think, this is really the intuition. Right? Now, if you want to make this precise, this is what you have to write. So this is a crucial definition which is going to underlie all of our arguments. In fact, historically, it took some time for this definition to emerge. It looks very simple, but it really does miracles to the way you can write down arguments in random matrix theory. If you don't have such a definition and you try to write down things sort of more in a more pedestrian fashion, basically just unwrapping this definition and writing these kinds of statements at every line, the arguments become extremely messy. And depending on the complexity of your problem, everything becomes unreadable and completely unmanageable. So this really does simplify the arguments enormously. You will see how we use it. We will use it throughout this course. So now a remark, and this is something, this uniformity is a bit of a nuisance. We don't want to keep on emphasizing that things are uniform in these parameters U. So the convention, which is always going to be true, is that this stochastic domination is always going to be uniform with respect to all matrix indices and the parameter Z, the spectral parameter Z, which is the argument of the Skiltis transform or the green function. So this is something I will usually not even mention, but this is always true, without exception. Okay. So then some further notation. So now if we take a similar family X, the same kind of family, except now it's no longer non-negative, it can be a complex valued random variable. So we will write X. X is big O. So this is notation that is very analogous to the usual big O notation that you already know. So we write X is big O with respect to the stochastic domination of Y to mean that the absolute value of X is stochastically dominated by Y. Okay. So that's just a simple definition. It will be very convenient because you can sort of keep track of error terms and put them in these kinds of expressions. And finally, we will sometimes use the notion of very high probability. So the event. So suppose I have an event, in fact more specifically a family of events, which may even depend on a parameter U. And I will say that this event holds with very high probability if the probability of its complement is bounded by such an expression. Right? So my notion of very high probability is that the complement has arbitrarily fast polynomial decay in N. And there's a sneaky way of writing this, which I will use. I will do this to confuse you, but also to force you to think a little bit about this definition. And one way to write it, so 1 minus the indicator function of the event if this thing is stochastically dominated by 0. Okay? So you can stare at this a bit, and if you understand this definition, then you will see that this is exactly what I said in words. Alternative, I mean, if you wish, this really means that the probability of the complement of omega is bounded by this for any d, and it can be written in a short way like that. Okay, so you can, if it's not
something missing in the sentence.
Oh, the event. Yes, indeed. Thank you. This is not a great sentence. So the event holds a very high probability if Okay, I think now the sentence might even pass a grammar check. Good, thanks. There is, if you read in the literature, some authors call this notion of high probability, very high probability, they call it overwhelming probability. I just find the word unpleasant and also misleading, so I usually use this terminology. So, let me give you an example. We will see plenty of examples, of course. We will use this definition throughout the course. I will give you a simple example, and that is now, so we work always with our Wigner matrix. And for example, what you can prove is this. So that the entries of your Wigner matrix are stochastically dominated by 1 over square root of n. This is a very simple exercise. It's going to be on the next problem set. Basically, the exercise is you basically just have to understand what this means. You have to go back to the definition of the Wigner matrix, and you have to use Chebyshev's inequality, and that's about it. So I'll leave this as an exercise, but I think it's a very valuable one to get an idea for what this means and how these things work. And you see, this is a very simple and elegant way of writing a highly non-trivial estimate, which is an estimate of the kind we will use throughout the proof. It would be much more awkward to keep on having to write these kind of, for example, LP bounds. This ultimately results from the third part of the definition of Wigner matrices, which was bounds on the LP norms of the entry. But this is a much more intuitive and simpler way of writing basically the same thing. Okay. Are there any questions so far? Is it okay? All right. So let me. Yes. Was there a question? Yes.
Just formally for the definition of holding very high probability. So our set UN would then be like the Cartesian product of like the matrix indices and all omega in our underlying probability space. Like I have a bit of a hard time to see the connection.
Okay, so let me take an example here. Maybe that's a good thing you asked that. So let me say explicitly U. So n is what it is, right? Capital N ranges through the integers. Un, I think it's what you said, basically. So un. Okay, so I will use this notation throughout the lectures. So the first n integers I denote by brackets n. So little u is equal to and I think that's about it, right? Does this clarify it, or did you have? Was there some other part to your question that we didn't clarify? I think this makes the link right to the. Another statement. In fact, I will write down. Okay, I'll write down the main theorem of these lectures in a minute, which uses the same thing. So often we will have a set which is a bounded open subset of the complex upper half plane, and then U is typically going to be n to some power k times this set. And the entries un. And this Sn is going to depend on, this S is going to depend on n. And the elements are typically going to be so this, I think, is the most general form of parameters U that we will use in these lectures, or that basically anyone uses ever, anywhere. And everything will always be uniform with respect to all of these guys.
Now, I was only confused because I thought when it says negative families of non-negative random variables, I thought xn of u is already the evaluation, but xn of u is the random variable.
Xn of u, yes. Oh yeah, that's right. So in addition, of course, I say these are random variables. That means there is the random element as well, which as is customary in probability, I will always suppress. In fact, a further remark, since you asked, and I think this is a good thing to clarify. If you want to, if you worry about foundational things, and probably you should, what is the probability space? So on what? I mean, I talk about random variables, so I should be able to tell you what the probability space is. And there are two different philosophies in random matrix theory. One of them is good and one of them is bad. And let me give you the bad philosophy. At least, of course, you may imagine this is highly subjective and there are people who will disagree with me. The bad philosophy is that you have a unique probability space, omega, and these are all random variables on the same probability space. And so they are random variables which are indexed by n and u. Well, okay. The second point of view is also that okay, maybe I should not say a single probability space, but you see, for example, here, let me put it this way, this would be, or C, and okay, so you would have an infinite matrix, an infinite square array, and for example, your entries, when you give yourself an n, you would just pick your matrix to be formed from the n by n upper left block of this infinite array. So this is something one can do, and one does. This is somehow a very, very artificial situation. Why? So we have a sequence of matrices. We have a 2 by 2 matrix, a 3 by 3 matrix, a 4 by 4 matrix. Why should these guys be increasing? Why should the top left 2 by 2 block of the 3 by 3 matrix, why should that be the same as the 2 by 2 matrix? There's no reason why it should be the case. So the good way to think about this is that you in fact have a different probability space for every n. So we would have a sequence of probability spaces with sigma algebras and probability measures. So for every n, you have a new probability space. And if you wish, of course, you can put all of these together. I mean, you can form you can take the union, you can take the disjoint union of all of these guys. I think this is the customary notation. So you take the disjoint union of all of these probability spaces, and that would be your probability space. So this is the good point of view. This is not really useful. I mean, you can do it if you wish. This is not really useful, but when I write things like P, this is what I mean. And I think this is the good point of view, and this is what you should keep in mind. Does this make sense? I hope this. So this is sort of, if you want, this is philosophy, but I think it's actually helpful to have this in mind. Okay, so let me, so as I said, this is going to be an exercise. So again, I illustrate this convention. When I write something like this, the underlying assumption is this is uniform in I and J. If I don't state it, everything is always by default uniform in I and J. So let me now give the main result of these lectures. So I will start. So there are many ways of structuring lectures of random matrices. The classical way is to start proving the semicircle law using the moment method. And if you know about that, you You may have seen it in some, if you've heard about random matrices before. To be honest, I find it slightly dull, so that's why I didn't do it here. And I'm starting with something that is much more, in fact, is much stronger than that, and I think is also much more interesting and has far deeper implications. And that is the following result, which is called the local law. And so it looks like a technical result. In some sense it is, but it has very far-reaching consequences in random matrix theory. So this is a local law. It's called the local law for Wigner matrices. In the past 10 years, basically, people have understood that local laws are the key that unlocks basically any non-trivial question about random matrices. If you want to analyze almost any non-trivial question about random matrices, this is the most important thing you have to understand first. There are other steps as well, which we will discuss in the second half of the semester and also next semester, but this is the most fundamental tool that you need. So what is the statement? So I will fix some positive number tau, which is positive and cannot depend on n. So if I write fix, it means things cannot depend on n. And I will define this subset that I called S, this one here. So it's going to be a subset of the upper half plane where my spectral parameter Z will be allowed to lie. So it's often called the spectral domain because it's the domain of Z, and Z is called the spectral parameter. So I usually abbreviate it by S. You know, just like if you have functions f of x, you don't necessarily always write f of x, you just write f. Or if you have random variables, you don't write x of omega, you write x. So I usually also suppress the dependence on the various parameters, but this depends certainly on tau. And it also depends on n. So for every n, according to this philosophy, I will have a new probability space and I will have a new spectral domain. So this is going to be the set of complex numbers. And I use the following convention for the real and imaginary parts, e plus I eta, which I think I introduced last time. So I will always use these symbols for the real and the imaginary parts of Z, such that, so the real part is bounded by 1 over tau. So the idea is tau is small. The smaller tau is, the stronger the statement. So you should think of tau as being a very small number. In other words, this can be very large. And eta can go up to 1 over tau. So again, eta can go up to a large number. But the most interesting and important condition in this definition is the lower bound on eta. So eta has to be bigger than n to the minus 1 plus tau. If you recall from last time, the smallest value of eta for which we have any hope of controlling the Stieltjes transform of mu is an eta, a spectral scale, which is much bigger than the separation of the eigenvalues. And that was 1 over n. So in other words, this is the optimal scale up to tau. So if you make tau very, very small, this is the smallest scale on eta which you can hope to show that, for example, G is well approximated by n. We know that below that scale this is not going to work. So we take this scale and tau should be made as small as possible. So then the claim, so maybe I should draw this. So it's the following domain. So it's a very simple domain. It's a rectangle in the complex upper half plane that comes very close to the real line. Okay, so then I would like to give the statement, but maybe I should do that after the the break, since we have a break now. So let's have a break, and I will give the statement of the theorem after the break. Okay, so let's continue. So I would like to now formulate this statement. Aha, this is probably not the right word. So this was a theorem. I don't have any statements labeled local. So we take a Wigner matrix. So then the claim is the following. If you recall, we have the Stieltjes transform of mu, so the eigenvalue density. And the claim is that this thing is going to be close to this simple deterministic Stieltjes transform M of the semicircle law, plus an error term. And this error term can be written very conveniently in the following way. So I remind you, Z is always, so if you want to, you can regard eta and E as functions of Z. So this is just the imaginary part of Z. And so this is in the sense of the stochastic domination. And so let me give this a name. And this is going to hold uniformly for Z in S. So here the parameter U in the stochastic domination is just this Z, which lies in this uncountable set S. So this is one statement. And another one is you could ask, okay, so this is in terms of the Stieltjes transform of the empirical eigenvalue measure. If you recall, this was the normalized trace of the green function. You could ask, well, what about the green function itself? And one can be more ambitious, and in fact, we will see for the applications, for many applications, almost all of them, it's not enough to control just the normalized trace. You have to control the green function itself as a matrix, so the individual matrix entries of the green function. And one can do this as well. This turns out is close to the most naive thing you could imagine, which is the identity matrix times this. So this is the trace of that guy. So what is this guy going to be close to? Well, in fact, it turns out it's equal to this guy times the identity. Now, as you might imagine, this object is obtained by taking the trace, the normalized trace of this. So this is an average. So whatever error parameter you have here, it's probably going to be worse than this one. Right? If you recall the central limit theorem, for example, if you take a large number of random variables which are not too dependent, then their average is going to concentrate much better than the individual random variables themselves. This is an average of that, so you would expect them to concentrate better than this. So you would expect whatever error parameter I put here, it's going to be worse, it's going to be bigger than this one. And this is indeed true. It's an error parameter that I call psi of Z. I'll give it in a minute. I'll define it in a minute, so let me first say, so this holds uniformly in I, J goes from 1 to N, and Z in S, where what is this psi? Psi was defined, or is defined, defined by the following object. So it's the same thing as here, but you have another thing. You have the square root of 1 over n eta. Remember, eta is much bigger than 1 over n. So this is always a very small number. So here you are taking the square root. So a priori, this term should dominate. However, in some circumstances, this imaginary part is going to be small. So sometimes one or the other dominates. Now, this might look a bit strange, this error term. There are a few things I want to say about it, and this one as well. So this is optimal. Both of these bounds are optimal. In other words, there does not exist a deterministic function and a genuinely different deterministic function such that this, or genuinely smaller deterministic function such that this is true. So that's the best you can do. And we will see in the duration of this semester how these error terms crop up, and indeed we'll get a feel for why they are optimal in different circumstances. So this is a statement. So for now, this one is much easier to interpret. In fact, I would like to give a heuristic interpretation of this, including the error term. But basically, you see, it says that this Stieltjes transform G is well approximated by M, and the difference is small. This is a small number, provided eta is much bigger than 1 over n, which it is. And in fact, one can make this, there's an interesting, slightly more detailed discussion one can do, and that's what I would like to do now. In fact, so I will do it for the first one. In fact, one could do exactly the same kind of discussion for the second one. One would get the same conclusion. It's just a bit more annoying to analyze because the error term is more complicated, but the conclusion would be the same. But let me just do it for the first one. So let me take this term here, and this estimate here, and consider its imaginary part. So I know that the imaginary part of G of Z is equal to the imaginary part of M of Z plus if you recall, if you want to get the imaginary part of the Stieltjes transform has a much easier and graphic interpretation than the real part. So let me just look at the imaginary part. So this is what you get by taking the imaginary part, and this tells you, if you recall what we discussed last week and also the problem set of last week, this says that mu, right? So mu, this is the Stieltjes transform of mu. In fact, when the imaginary part of Z is close, this is very close to the density of mu. And this was the Stieltjes transform of rho. If the Stieltjes transforms are close, then so are the measures. So let me make this comparison a bit more precise by analyzing the density of the eigenvalues. So let me recall the semicircle law. So this result says that the density, the mu, the empirical eigenvalue measure, is close to this density rho. So the density of the eigenvalues is typically proportional to this, the height of this guy times n. So in particular, it means that near the center, the eigenvalues are very dense, and as you approach the edge, they become less dense. Right? Near the edge, they are less dense. And one can try to figure out what is the typical separation between these eigenvalues. So the density So the density of the eigenvalues at E, so let me pick a number E here. So this is of order so the number of eigenvalues, if you want to be a bit more precise, the number of eigenvalues in some interval I is equal to mu of I, right? That's by definition, in fact, times n. That's by definition the number of eigenvalues in the interval I. And now if I say that this thing is approximately rho of I times n, so if I want to find out the density, I divide both sides by the length of I. Okay? So this is the density of the eigenvalues, and now I can compute. So what is the density of eigenvalues? I will use this symbol, which I think is a quite commonly used asymptotic symbol, so maybe I should introduce this symbol. So I use this asymptotic notation. So this means of the order of, to mean that there exists some constant, some positive constant, typically large, such that an is bounded from above and from below by bn up to this constant c. Okay. This is the notation I use, and this object, now you can just look at the definition of this density rho. It has a nice continuous density, and I ignore factors of 2 pi which go in here. In fact, this is equal to this, what I'm going to write. Up to a factor of 2 pi, which I don't care about, and I put it in here. Okay. So let's try to figure out from here what the typical eigenvalue density is, and I will in fact consider 2 cases. Which are, if you look at any random matrix theory book or anywhere in the literature, people are always talking about 2 different types of statistics. One is the so-called bulk, and bulk refers to the fact that you are inside the spectrum, for example here or here. And the other one is the edge, which refers to the fact you are at the edge of the spectrum. And things look very different depending on whether you are at the edge or in the bulk. So let me first talk about the bulk. So what does it mean? It means we fix an E, which means it cannot depend on n. It's somewhere in the interior of the interval -2, 2. That's what it means to be in the bulk. And the density, now this number is a fixed number. It's a fixed positive number. So the density is proportional to n, right? It's of order n. And therefore, the spacing is proportional to 1 over n. Right? If you have a density, if you have a location where the density of eigenvalues is of order n, that's spacing, so the typical distance between 2 consecutive eigenvalues is 1 over n. This means that the imaginary part of g of z is equal to the imaginary part of m of z which is of order 1. This is a simple exercise to check. In fact, if you did on the homework set, you worked out what this thing is when eta is very, very small. You saw that up to a factor 1 over pi, this thing converges to the density, right? To the density of the measure, which is given by this number, which is strictly positive. And I can write it as 1 plus little of 1. Because this number is small. Eta is much bigger than 1 over n. Provided if eta is much bigger than the spacing. So this much bigger than, so this is a heuristic discussion. So I use these kinds of symbols. I only use these in heuristic discussions. You should read it as being much bigger than. And if you want to make it more precise, you could say that this divided by that tends to infinity, or is like n to the epsilon for some small epsilon. Okay, so this in the bulk gives a clear picture of what's happening. So we can approximate. So in other words, this Stieltjes transform, the imaginary part of this Stieltjes transform, is equal to the imaginary part of the deterministic Stieltjes transform up to a negligible multiplicative error. And this is true on any spectral scale, eta, much bigger than the eigenvalue spacing. That's kind of the heuristic that we saw last time. And this is apparent in the statement of this theorem in the bulk. Does this make sense? Is it all right? So it's very instructive to do the same thing at the edge, because the same qualitative conclusion is true, but the scales involved are different. And indeed, the edge behavior of random matrices is completely different from the bulk behavior. So let's work out, let's do the same heuristic argument near the edge, or at the edge. So this would be then the edge. So what does this mean? It means that you take an E, now the real part of Z that you are considering is not here, but it's right here. It's at the edge of the support of the semicircle wall. So let's do an analogous calculation. So the number of eigenvalues, in, let's compute the number of eigenvalues. So this was 2. Let's compute the number of eigenvalues in this small interval, which goes from the edge down into the bulk, slightly into the bulk, by a distance x, which will be very small. So x, let's say x is 0, 2, something like that. So we don't want to go all the way to the other edge. X, you should think of x being a small positive number. So this is equal to, approximately, if we assume this approximation of mu by rho to be correct, this is equal to the integral from e minus x to e of n times rho of dy. Okay, so this is, in fact, maybe I should write it, this is equal to n times the integral e minus x e mu dy. So this is by definition of the empirical eigenvalue measure. This is inequality, and now if I heuristically I make this assumption that mu is well approximated by rho, I get the following object. And now if you recall, rho had this form. So this is the thing we are trying to compute. And this is an integral. In fact, you can do it. I mean, you can do this explicitly, right? You will get some, what do you get? You get some arc signs or something like that, or you do a, I mean, you can do a substitution. But we are only aiming, we are doing analysis. We're not doing algebra here. So you can in fact say that this guy behaves like square root of 2 minus y. Okay, You can write it like 2 plus y. You can write this as 2 plus y times 2 minus y. And 2 plus y is bounded from above and from below by some positive constant. So you can ignore it, put it in here. This behaves like that. And then you can just integrate this. And how to integrate the square root function is easy. You get the function x to the 3/2. So in other words, this thing behaves like n times x to the 3/2. Okay? So this is all rigorous. This is a rigorous calculation. Of course, this approximation is the heuristic one. But we're just trying to figure out what is the typical density of the eigenvalues around the edge. So what does this say? This says that the typical, that the number of eigenvalues as you go down from here, it goes like x to the 3/2. So where is the first eigenvalue going to be located? It's going to be located when this number reaches 1, right? The second eigenvalue is going to be located at the x when this number is equal to 2, right? So the spacing of consecutive eigenvalues, the x you have to go, so when is, so this, to get the spacing, you have to ask yourself, by how much do I have to change x for this number to change by 1? And the answer is by n to the minus 2/3. Okay? So by how much do I have to change, again, by how much do I have to change my x such that this number changes, let's say, goes from 1 to 2? The answer is by an order n to the minus 2/3. And this is in fact the correct answer. So this heuristic argument gives the correct answer. And indeed it is true that the typical spacing of the eigenvalues near the edge is n to the minus 2/3. We will see later on in about a month a very precise result. In fact, that's a simple corollary of the theorem that we just stated that tells you precisely how the eigenvalue spacing changes as a function of where you are in the spectrum. It goes from n to the minus 2/3 to n to the minus 1, depending on where you are in the spectrum, and that's sort of a smooth transition of scales going from n to the minus 2/3 to n to the minus 1. But let's just look at the extreme case of the edge. So now we know what the eigenvalue spacing is. We would like to get a similar statement. We would like to prove exactly the same thing. So in order to prove this, we have to understand how the imaginary part of m of z behaves at the edge. So I claim that the imaginary part of m of z behaves like square root of eta. So if you are at the edge, this thing behaves like square root of eta. And in fact, on the next problem set, you will have well, on the next one or the one after, probably on the one after, you will have an exercise which works out the behavior of this thing in generality, anywhere in the spectrum. Here at the edge, it's very easy. Why? So what is this object? Just go back to the definition of the Stieltjes transform, this fundamental calculation we did last week, and you will observe that that what you have to compute is, if you recall, you can take the explicit imaginary part of m of z, and you have to compute essentially the following integral. So this is, I leave the exact details as a little exercise, but this is basically the integral you have to compute. The square root of x is the same square root as here. This is the behavior of the density near the edge. You have so-called square root decay, which is a very characteristic feature of many, many random matrix models. Basically all of them, if you have such an edge, they basically always behave like square root of x near the edge. And this is what you get when you take the imaginary part of 1 over z minus 1. And this is an elementary, this is an integral. You don't even have to compute it. You can just do a change of variables. If you replace x by eta x, you will see that you get some universal integral times square root of eta. Okay, so just by a simple change of variables. So this means that the imaginary part of g of z is equal to the imaginary part of m of z, and I would like to write this again as 1 plus times 1 plus something. So in the actual theorem, I have imaginary part of m of z plus big O, stochastic domination of 1 over n eta. And here I pulled out this imaginary part of m of z, which is of order square root of eta. So I have to divide by 1 over square root of eta. And this now is precisely of the same form as before. When is this thing small? This is small when n times eta to the 3/2 is much bigger than 1. And this again is precisely when eta is much bigger than the eigenvalue spacing, which is now n to the minus 2 over 3. So we get exactly the same conclusion. So this somehow served as a hint that the error term we had, this 1 over n eta, is really optimal, and it's optimal both in the bulk and at the edge. And in fact, it's optimal everywhere. So this was a heuristic argument. I think it's a very useful one to give you an impression of what's going on, and it also describes the generic behavior which is apparent in almost all random matrix models, not just these Wigner matrices. Okay, and as I said, so we did this for this equation number 1. If you would like, and this is a valuable exercise, you can do exactly the same heuristic argument for equation number 2. And you will see that you get exactly the same heuristic. In other words, the approximation, let's say for the diagonal entries, GII, is valid precisely, it's valid in this sense. So this is well approximated. The GII is well approximated by m of z in this sense precisely when eta is much bigger than the eigenvalue spacing, whether you are in the bulk or at the edge. Okay, yes? A question?
Can you repeat how you get the additional 1 over square root of eta?
You see, I pull out this guy. I proved that this imaginary part of m of z is of order square root of eta. Okay? And if you look at this statement, which I start from, the right-hand side is this guy plus that. Now, if I pull out this guy, then I have to divide. I mean, if you want, I put in an imaginary part of m of zeta divided by square root of eta, which is 1, which is of order 1. Okay. Any other questions? Is this clear, this heuristic argument? It is heuristic in the sense that I approximate mu by rho, but in fact, this essentially the theorem that I stated will serve as a rigorous justification for all of these heuristic steps, as we will see. Okay, let me give one final remark. So we will, now there's always a choice when presenting results, is you present a big theorem, and this is a big theorem. Do you prove it first, or do you give applications first? And what I would like to do is to prove it first. The problem, of course, is that then you might not be convinced that this is such a great result. If I gave you the applications, then I'm sure you would all be in awe at the power of this theorem. But we will postpone that for probably next month. And what I would like to do is prove this theorem. And I am hoping that my advertising campaign is sufficient for you to believe that this theorem is of some importance, and that the proof is worth actually spending some effort on. And the proof is a very interesting argument. It's also the prototype of proofs of this type in random matrix theory. I think there have been at least 100 papers and a number of books basically proving these kinds of results and using exactly the ideas that we will use. So it's worth going through them carefully. The ideas are also very powerful and they are very nice. Maybe just before doing that, before starting the proof, I would like to make a remark which will play a certain, not a very important, but a certain role in some of the following applications. And it goes back to what I said about this uniformity in stochastic domination. That a uniform bound is not the same thing as a simultaneous bound. So I would like to make that a bit more explicit. So I told you that in general, if you have a uniform bound, saying that with very high probability, some random variable x is bounded, let's say x of u is bounded by y of u. And this holds for all u with very high probability. This is not the same thing as saying that for all u, x of u is bounded by y of u, and this holds with very high probability. So whether the for all u is inside the probability or outside the probability is a different statement. And inside the probability is a stronger statement. So in general, the weaker statement does not imply the stronger statement. In this case, it does. And that's an important observation. So this, in fact, implies the strongest simultaneous bound. So let me take, for example, you can do it both for the first equation and for the second equation. I will state it for the second one. So just to recall, what does this say? It says that gij of z minus m of z times delta ij. It says that this thing is stochastically dominated by psi. And this holds for all z. What it does a priori not imply, so what it intuitively says that this thing should be bounded by 1 for all z. What it does not imply is this statement, at least a priori. So this is a stronger statement. It says that you can take all these random variables, you can take the supremum over an uncountable set of random variables, and the result is still bounded by 1 with very high probability. In fact, this does follow, and in general, this is completely false. If you have a stochastic process, this implication is completely false. The reason it holds here is that there's a very special, these things have a very special property, which is a Lipschitz continuity. All of these quantities, everything I write on the board is Lipschitz continuous with Lipschitz constant bounded by n squared, for example. And this can be used to deduce such a statement. So this is basically an exercise in using Lipschitz continuity and understanding the definition of this thing here. So this is going to be an exercise with hints on the next problem set. It's a very instructive argument. It goes by the name of a lattice argument or an epsilon net argument. And these kinds of arguments are used a lot in many different areas of stochastic processes. They are a backbone of the theory of Gaussian processes, for example. They are used a lot also in random matrix theory, generally in high-dimensional geometry. And this is a particularly easy type of such an argument, so it's anyway very instructive to see and work through one such argument yourself. So this is going to be on the next problem set. Okay, but I will not go through the proof now, but is it clear why this statement is first of all different and why it is stronger than the statement number 2 in the theorem? So if you've studied some stochastic processes, this should be, I think you have seen this, and if not, you can just, or should I explain a bit more, or is it clear to everyone? Okay, if you want to, you can ask, yes?
But what is it uniform in?
There's nothing left. There's nothing left to be uniform in. This is just one random variable, because I took the supreme. Yeah. So in some sense, this notion of uniformity that we put in the definition of Prec is there because we cannot usually afford to have these kinds of very strong statements. Usually this just doesn't work. And that's why we need to add parameters, but nevertheless we have to make sure that things are uniform in these parameters. Okay, so let me now start the proof. So this is the next section. And this is going to be a lengthy section. The proof is not it's not completely straightforward. However, it is very conceptual. And just this theorem has been proved, just for Wigner matrices, has been proved about 10 times in the literature, each time with slightly more general assumptions and slightly slicker proofs. And the initial proofs, which came about 10 years ago, they were basically unreadable. They were extremely nasty, really, really very nasty. In fact, they were of the kind that I think no one ever read them, some parts. They were written, but they were so technical and hard to read that I think they were probably not read. And one of the progresses in this world is that we have now come to versions of the proof which are actually very conceptual and quite clean and can be easily presented in a basic course such as this one, and that's what I would like to do. So the proof well, of course, we are using this result throughout the course, so we will have to prove it, but the proof itself is also very instructive. It uses lots of nice ideas, powerful tools that are generally applicable in many different contexts. So let me start by a section of preliminaries where I will collect a bunch of tools which we will use, tools and notations which we will use throughout the proof. The first one, so these are tools from, well, we are doing random matrix theory, so it's probably not shocking. We will have tools from basically 2 areas of mathematics. One is linear algebra, and the other one is probability theory. So that will be basic tools from linear algebra, and that will be basic tools from probability theory. Now, linear algebra in principle is not a difficult subject, and we all basically know it. Nevertheless, there are some identities of linear algebra which you might not know if you haven't studied these problems. So I would like to give them, and I will start with the following. This is just a definition. So I will take, this is the notion of submatrices, so it's going to be very important to work with submatrices of my matrix. So I will choose a set T. T is going to be a collection of indices which I want to exclude from my matrix. So I define the following matrix H with superscript in parentheses T, which is just going to be my original matrix. So the entry is Hij, but I and J are now restricted to the set of indices without t. Okay, so if you want in matrix representation, if my set T would be this one, maybe this is my set T, I will eliminate all the entries in these rows and in the same columns. Okay, so this H is going to be a new square matrix, which is only these white areas. What remains in the white areas after you remove all rows and columns indexed by the set T. Okay, so this is the definition of HT, and then I will define the green function. This is the green function of HT. Okay, simple notation. Note that this is not what you get if you take the green function of H and you apply this process. These things do not. This process does not commute with taking the inverse. So you first have to get rid of the rows and columns, then you take the inverse. It's not the same thing as first taking the inverse and then getting rid of the rows and columns. Okay. And then finally, I will use this notation, which is convenient. So if I have a sum over indices with a superscript t, it means I sum over all indices which are not in t. So this denotes sum. And then I use the convention. So very often, in fact, in most applications, if not all, T is going to be a set consisting of just one index or two indices. And then I would like to abbreviate. So if T is a set of just one index, instead of writing these double parentheses, I will just write it like that. And so on if I have two indices. Okay. Is this clear? This is just linear algebra. Then a probabilistic definition. This is conditional expectation. I will define a linear map. In fact, it's an orthogonal projection in the space of random variables, in the L2 space of random variables, which I call Pi. And this is applied to a random variable x. And this is by definition equal to the conditional expectation of the random variable with respect to hi. Okay, so this is the definition of Pi. Now, if you know conditional expectations, I mean, this is, in some sense, well, this is an very easy version of conditional expectations because everything is independent. So if you know conditional expectations, you know that this Pi acts on, it gives you a new random variable, and it's an orthogonal projection, so Pi squared is equal to Pi, and it's orthogonal in the L2 space of random variables. In a very pedestrian fashion, what this thing does, it integrates out the random variables in the ith row and column. So it does not touch the random variables which are in the other rows and columns, and it integrates. So if you want to, because all the randomness they are independent, the ith row is independent of the I plus first row. So this, you can just view this as taking the integral over all the random variables in the ith row and column. That's exactly the same thing. So if you want to, you can think about it in that way. This is a slightly more compact, and if you want a professional way of writing what I just said. If you haven't seen conditional expectations, you can just go to some basic book on probability and read up on it. It's not a very hard thing, but again, we will not need most of the subtle facts about conditional expectations, which is when you're taking conditional expectations with respect to events of measure 0 and so on. This is all much more sophisticated. This is a very basic, the most basic notion of conditional expectation, and that's going to be sufficient for us. Okay, so let me stop here. We will continue next week with these preliminaries and then get into the proof itself. Now, I guess there's a break, and then Johannes will start with the first exercise session.